Imagine a baking loaf of raisin bread. As the bread rises, the raisins move farther apart. They aren't moving through the dough itself is expanding. That's a lot like our universe. It's not that galaxies are flying away from each other through space, it's space itself that's stretching, pushing everything farther apart. This expansion, discovered in the last century, was a revolution in our understanding of the cosmos. It means the universe isn't static, it's dynamic, alive, and constantly changing. And this change has profound effects on everything in the universe, even light itself. Think about it. If the universe is always expanding, then that means it was once smaller, right? Much smaller, in fact. Everything we see today, all the galaxies, stars, planets, even us, were once crammed into a tiny, incredibly dense point. That's the mind-blowing beginning of our universe, the Big Bang. Now, let's talk about waves. We see waves all the time, in the ocean, in the air as sound, and even light itself travels as a wave. Waves carry energy, and this energy depends on the wave's length. We call this wavelength. Imagine the waves in the ocean. Short, choppy waves carry less energy than long, rolling waves. Light waves work the same way. Different colors of light have different wavelengths. Blue light, for example, has a shorter wavelength and carries more energy than red light, which has a longer wavelength. It's like the difference between a gentle push and a hard shove. But here's where the expanding universe comes in. As space expands, it stretches out the light waves traveling through it, just like the markings on a rubber band would stretch if you pulled it. This stretching increases the wavelength of the light. Remember how we said that red light has a longer wavelength than blue light? Well, as the universe expands and stretches light waves, it shifts the light towards the red end of the spectrum. This is called redshift. It's like the universe is playing a cosmic game of red light, green light, but everything's shifting towards red. Redshift is how we know the universe is expanding. When astronomers look at distant galaxies, they see that the light from those galaxies is redshifted. The farther away the galaxy, the greater the redshift, which means the universe is expanding faster the farther out we look. Redshift isn't just some abstract concept. It's a powerful tool that allows us to map the universe and understand its history. It's like a message from the distant past, telling us about the universe's incredible journey of expansion. Section 4. When light gets tired. Now you might be thinking, if the universe is stretching light waves, what's happening to the light itself? Is it getting weaker? The answer, surprisingly, is yes. You see, light is made up of tiny packets of energy called photons, and just like waves, photons are affected by the expansion of the universe. As space stretches, it stretches the wavelength of photons, making them less energetic. It's like a long-distance runner. The farther they run, the more energy they expend, and the more tired they get. Similarly, photons lose energy as they travel through the vast expanse of space. This energy loss is a direct consequence of the universe's expansion. It's a subtle but profound effect that has implications for our understanding of the universe's energy budget, a cosmic accounting ledger that we're still trying to decipher. Section 5. The case of the missing energy. So, where does all that energy go? It's not like it just disappears. Energy, as we know, cannot be created or destroyed, only transformed. So if photons are losing energy, something must be gaining that energy, right? That's where things get really interesting. You see, space itself isn't empty. It's teeming with quantum fluctuations, tiny bursts of energy that pop in and out of existence. These fluctuations are like the background noise of the universe, a constant hum of energy that permeates everything. And it turns out that these quantum fluctuations are the culprits behind the missing energy. As photons lose energy due to the universe's expansion, that energy is absorbed by these fluctuations, fueling the cosmic hum. Section 6. Space. The ultimate energy thief? Think of it this way. Imagine you're shouting in a large, empty room. Your voice carries energy, but as the sound waves travel, they lose energy and eventually fade away. Where does that energy go? It's absorbed by the walls of the room, ever so slightly raising their temperature. In a similar way, the expanding universe acts like a giant room, absorbing the energy lost by photons and other particles. Space itself becomes the ultimate energy thief, silently siphoning energy from everything traveling through it. This constant energy exchange between particles and space is a fundamental aspect of the universe's evolution. It's a delicate dance between matter and energy, governed by the laws of physics and shaped by the relentless expansion of space itself. Section 7. The universe's grand energy exchange. The universe is a vast and mysterious place, full of wonders that we're only beginning to understand. The expansion of the universe and its impact on energy is just one example of the intricate and interconnected nature of the cosmos. As we continue to explore the universe and unravel its secrets, we're bound to encounter even more mind-boggling phenomena that challenge our understanding of the laws of nature. But one thing's for sure, the universe is full of surprises, and the journey of discovery is far from over. So, the next time you look up at the night sky, remember that you're witnessing a grand cosmic ballet, a dance of expanding space, shifting energy, and the endless interplay of matter and the void. And who knows what other secrets the universe holds, waiting to be uncovered.